Yeah, we are going to cover static equilibrium by solving a couple of problems today. So this is our today's agenda. So if you are all ready, let's get started with the discussion. So just let me know if you cannot, read anything on the board because it's kind of messed up right now. So static equilibrium. So what is it? Let us just summarize the mathematical equations that give us this condition. Suppose I have this fancy potato, okay? So I need to remember that as for the initial conditions of this object, I'm going to assume 0 initial velocity for the center of mass. So this is our initial condition. And this potato is not to be rotating or anything initially. Okay, now for the time evolution, for the later state of this potato, we are going to write down the Newton equation of motion for the external forces as well as the torques. So we have the sum of all the external forces equal to mass times the acceleration of the center of mass, and sum of all the external torques or moments as we like to call it in the business. This should be equal to moment of inertia times the angular acceleration. For static equilibrium, we are going to assume that the left-hand sides are equal to 0. And of course, to be more precise, these are all vector zeros. This means we have acceleration of the center of mass equal to 0 and the angular acceleration of this potato equal to 0, which means we have constant velocity vectors for the velocity of the center of linear velocity of the center of mass as well as the angular velocity of the center of mass for this object. So they are constant, and since they are constant, they must be equal to what? Anyone? Using the initial condition that we assumed over there. Zeros. If you know the initial condition and if you know that your vector is a constant, it should follow its initial value throughout the time. Right? That is what we are doing. Okay. Now, this is our mathematical structure to analyze the following problems. We have 4 problems, and they are really nice problems. So let's just go over them one by one. So the first example is called book on a table. So what do you mean by that? Suppose this is the ground level. Okay, suppose we have this table over here. And I'm going to put some book right here. Okay, let us assume that the mass of this book is uniformly distributed throughout this body. So it will be at the geometric center of this book, right? It's a rectangular shape, so it will be half of the base, half of the height. We are given that the length of this book is capital L, and the mass is given to be m. And the question is, given that this distance is L, namely the distance from the edge of the table to the edge of the book, lowercase l, what is the largest value of l, lowercase l, so that this book doesn't just tip over the table. This is the setup. Okay, intuitively, we know that if this L is larger than halfway through, it will tip over, right? Because of the uniform uniform mass distribution. So the center of mass will be right at the center. And even intuitively, if you put more mass on this portion than here, it will tip over, right? So we are going to show this mathematically. So let us do the two cases separately. The first case is this lowercase l is less than half of the entire length of the book, which is capital L. Now what happens? Now let us just focus on the book here, and we have the table here. So the center of mass is here because this is less than half of the length. And I'm going to assume the following coordinate system. To the right is positive x, and upward is positive y. Now, okay, actually let us put it right at the edge, because that will be more illustrative for our purposes. Now let us isolate this book to identify the external forces acting on it. Just going to slightly up. Okay. So at the center of mass, we have the weight, the gravitational force due to the mass of this object, which is m times g, right? And we have the contact force, the normal force, pointing in the upward direction. Now, in this condition, with this setup, we require this object to be in static equilibrium. So let us write down the force condition. The sum of all the external forces should be equal to 0. Since we just have forces along one direction, we can just specify a direction using like verse, up and down. So I'm going to assume the upward to be positive for this convention. So we have n as a positive contribution to this summation, minus mg is a negative contribution, so this must be equal to 0. Therefore, we have n, the normal force acting on this book due to the table, equal to m times g. Now let us write down the torque equation. So we want the sum of all the external torques to be equal to 0. We are going to use the clockwise and counterclockwise directions for the torque because this is just a two-dimensional problem. We are on the xy plane. So all meaningful torques could be either counterclockwise or clockwise, right? There are just two possible directions for the torques here. So I'm going to remove this arrow here. I will treat it as a scalar, and as for directions, I'm going to assume counterclockwise to be positive. Okay, now let us assume that this part from here to here is some distance r. So for the summation, for the sum of all these external torques, let's see what do we have. So I'm going to quickly reproduce the figure over here. We have the center of mass here. We have the y-axis, the x-axis, and this is the edge of the table. So we have this normal force, at the tip of the Okay, sorry for the quality of the board. Okay, this is normal force, and we have the gravitational force acting on it. Is that an accurate picture for the location of the forces? Like, should I maybe put my force at different points on my body? So this is a very tricky question, because I try to play trick on you. If you go back to this figure, we see that all the forces are acting at the center of mass, right? So I intentionally put that normal force at the edge of the table, just to confuse, and there was no objections so far. Huh? I'm sorry, I couldn't get that.
So like, assume you have like a lower, like big L minus smaller L,
Uh-huh.
and then you put that in the middle of like L minus L?
The portion hanging to the from the edge of the book is that length is less than half of the entire length of the book. So there is no chance for this book to tip over yet. That's the configuration.
Right, but shouldn't the normal force be towards the left?
No, because this is a very good question. We have this perfectly horizontal table, and we have this object, and if there is any force in the direction other than the vertical force, this guy is going to move.
No, I was just saying that it will be vertical up, but shouldn't it be like acting on?
It's a center, exactly, yeah, that was the trick part, yeah. I did that intentionally just to make sure that everyone is listening. Okay. Cool. Now let us write down all the forces about this pivot point. So this is our critical point, right? If there is let's say too much moment or torque about this point, this guy will tip over. So remember at this distance, this is R. Okay? So we have the normal force trying to create a torque in the clockwise direction, right, about this pivot point. So since it is clockwise, it will come with a minus sign. So we have force times the moment arm or torque arm. And we have this mg, the gravitation for the weight, trying to create a torque in the counterclockwise direction, which is a positive contribution to this summation. So we have force times the moment arm, R again. So we have minus N minus mg times R. But from the condition on the forces, we already know that N is equal to mg. So the expression in the parentheses will be equal to 0. Therefore, we don't have any net torque acting on this object. So this object is perfectly in static equilibrium. Very simple, very basic example, but I think very illustrative. Now with that, we are going to study the second case. When this distance by which the book hangs off the table is greater than half of the length of this book. So we have, okay, let's exaggerate the picture. Okay, so this is the edge of the table, tip of table, and this is the center of mass. And even intuitively, this is about to, this book is about to fall off. Now we need to see that right before it falls off, there will be a contact point here, right, at the tip of the, at the edge of the table. So that was the trick I tried to do here, because there is this entire contact here, but there will be only a contact point right here when it is about to fall off the table. So we can assume that it is already leaving the table, the figure like this. Okay, now let us put another coordinate frame here. Assume to the right is x, upward is y, and we have mg acting at the center of mass in the downward direction. And at this point, when we remove the table so as to isolate this book, we will have this normal force. Now, we are going to take this point, this tip of the table, as again our pivot point. And we will consider the torque equation, because from the previous case, we will have the same force equation, so n is still equal to m times g, because nothing changed regarding the external forces. So forces are the same, but we will be interested in the torque equation. So let us call this R again. And let us try to write down the moment equation, the torque equation about this point. So we have the sum of all the external torques, again, in the general case as a vector, but for this two-dimensional case, it is either counterclockwise or clockwise, so I'm going to assume counterclockwise to positive again. So let's see what do we have here. What is the moment of this normal force about this pivot point? Anyone? I know you know it. You have that type of vibe. Zero, right? Why? Because it goes right through this pivot point. So its moment arm is equal to 0. So we have n times 0. And now for the mg, the weight, we have this weight trying to create this clockwise torque with this moment arm of r. So we have minus mg times r, so the net torque will be equal to minus, so it is clockwise, the weight of this book times the moment arm. So this part is already L, and this is half of the length of the book. So we see that once this distance, lowercase l, exceeds half of the entire length of the book, it will tip over, and this will be the torque that will create this initial tipping. I'm going to say force in quotation marks, but actually it is a torque. So very nice, very illustrative example. Okay, now this is just the beginning. The other examples are kind of more fun. Okay, now we have something that concerns maybe the field of medicine, because whenever we talk about, or whenever I talk about static equilibrium, I immediately think about all the engineering and architecture applications. So this is a different example. So the case is like this. Okay, I messed it up. Suppose we have this object, and you are literally holding it like this. Your upper arm is vertical, and your lower arm is horizontal to the floor, ground level. And suppose this object weighs like 2 kilograms, let's say. We are going to try to understand what is going on here physiologically. Not in terms of medicine, but physically. So suppose this is your arm, this is your hand, and you have this object here with a mass given to be 2 kilograms, and you are just literally holding it. You have some bones here, there will be some elbow joint here, and you have other bones here. But there is this muscle group here that creates or that experiences some sort of tension that will help you keep that object like this in static equilibrium. And the question is, what is the force that develops in this muscle? And we are going to call it the force M. Okay, for this, for some simplifying assumptions, we are going to assume that our arm in entirety has no weight, so massless arm. Unless you are really into bodybuilding, which is not the case because it's at 2 kilograms. So compared to that weight, our arm is kind of massless. And we will assume that the arm length from the elbow joint to the object is, let's call it capital L. It is given to be 28 centimeters. And we are also given that this muscle group that that experiences some tension force to carry this weight is at a distance, let's say lowercase l, given to be 3.2 centimeters to the right of the elbow joint. So this is the scenario that we are going to analyze now. Okay, now it is again convenient to start with the force equation because we are just adding up all the forces that we see, and we want the net force, net external force, to be equal to 0. And that will give us that force this muscle group will experience. Okay, for the static equilibrium again, we have the sum of all the external forces equal to 0. Now, how do I attack the problem? Yes. It is the force that develops in this muscle group in your arm for you to be able to carry that object. It's a tension force. But that is just physiological details. As long as physics is concerned, it is just a force that tries to pull your muscle in the upward direction. That's it. Now, how are we going to attack this equation? So we need to isolate this picture so that we can write down some, or we can draw some free body diagram, right? So this is how we do it. We will assume this beam structure for our arm, and at the very end, at the tip, we have this mass. We have the weight of the mass, m times g. Easy. Then for this capital M force, the force that the muscle group will experience, we have this upward force, capital M, and this is the pivot point for all of our discussions, which is simply this elbow joint. Okay, this is known, lowercase l, this is known, capital L, and the values are over here. So this is our simplified picture for the sake of physics, right? We don't care about the physiology here. We just care about this structure, this simplified or equivalent structure. Now we have, again, let us, since it's a simple picture, and since we have all the forces in just one direction or one axis, let us assume the upward to be positive. So we have positive capital M minus m times g equal to 0, So we have this force in the muscle group equal to simply the weight of the object, which makes perfect sense here. And if you plug in the numbers, let's numerify everything here. We are just going to obtain, I don't think I have the answer now, but you can compute it easily. I'm just going to leave it here. Yeah, sorry for the numerical trouble here, but that's the idea. Now let us try to understand the torque equation. So what is going on in the other side of the medallion that determines our static equilibrium? Okay, now, I'm just going to keep this and remove everything else. So we now try to understand the torques. And that's our pivot point. And again, I will always assume the counterclockwise direction to be positive. So let us write down the total external torque or moment for this structure. We have uppercase M, the muscle force, trying to create a torque in the counterclockwise direction, right, with a moment arm of lowercase l. So it is positive in our convention. And we have the weight, mg, that is trying to rotate the arm in the clockwise direction, so it will have a negative contribution to this expression. And the moment arm is equal to L. Okay, if we solve this for capital M, we will see that from this equation, M is equal to what? M G capital L over lowercase l. So what is going on here? We have two different values for the force that the muscle group experiences here. So how can you justify this? And you need to remember that even though you are carrying an object like this, you are not moving it around, you are not doing any physical work, you are still doing some sort of work, right? Like physiological work, like some biological means for the work. So there must be something else involved here. Because if you hold an object like this for an extended period of time, you'll get tired. So there must be something going on. So how would you like to solve this or attack this problem? Any ideas? I appreciate any creativity here at this point. We start with the torque equation, because when you hold it like this, since clearly there's something going on with the forces, right? Even though you are not doing any physical work, you are still getting tired, so there must be some other type of force involved. And we are going to identify it by starting with the torque equation. So we are standing like this, and our arm is not rotating anywhere in any direction, right? So there must be at least a rotational equilibrium for the static equilibrium. So we should have started with this equation, obtain a value for the force for the muscle group, and then try to understand the problem in terms of the forces. That is my statement here. When you think about it like that, okay, here's our justification. There is physiological work involved here, so there must be other forces involved here. So the only thing that we can say is that our arm is not rotating. So at least arm is not rotating. So we should start with the torque equation. Okay, that's doable. Then where do we put the other force so that the system is in equilibrium, right? Because if you do it like this, L is certainly greater than lowercase l, because L is the entire arm, and L is, the lowercase l is just this distance. So this factor is larger than 1. So capital M is some factor that is greater than 1 times mg. So capital M is greater than mg. So we have more force in the upward direction than the down force. So there must be some other force that's pointing in the downward direction. Is this justification clear? Yes. Huh? One more time. So this guy is certainly greater than 1 because L is this distance and lowercase l is this distance. It is the distance of the muscle from the elbow joint. With this, capital M, that force in the muscle, is larger than mg because that factor is larger than 1. Say it is 2, or we can compute it, actually it's like close to 10. So we have this upward force M, which is greater than, a lot greater than mg. So we have, let's say, you can plug in the values to compute the actual number, but the numbers still don't matter as long as you see this factor. So there must be some lower force, some force in the downward direction missing in this picture. So where are we going to put that force so that our torque, our rotational equilibrium condition is not disturbed? Assume uniform distribution for the arm. So, but we said our arm is massless compared to the rest of it, but good idea. Anyone else? Like who likes to take a step? You put a force on this beam type of structure so that you satisfy the force condition, you solve the issue, and you don't mess with the torque equation, or rotational condition. So this force that you are going to put should create zero moment or zero torque. And where do you like to put it with this in mind? Exactly, thank you. So we have this guy missing in the first place. So let's call it F elbow. Exactly. Now you go to the force equation with this condition, and you can compute the force that develops in your elbow. Nice and easy. And since this guy goes through the pivot point, it will not disturb your rotational equilibrium. Very creative problem, right? I like this problem a lot. Questions? Comments? Okay, let's do the next one then. We are just getting more and more fun here. Okay, this is kind of a civil engineering problem, but at a very elementary level. Okay, it is the third example today, and it says locomotive on a bridge. So how many civil engineers do we have in the house today? Civil engineers? Yes? No? I was expecting at least one or two. Okay, that's okay. Cool. Okay. So you suppose you have this bridge that, of course, carries some railroad for the train to move, locomotive to move. And it is made of iron, and it has uniform mass distribution. So it is massive this time, unlike the previous example. Uniform mass distribution, and the mass is, the weight is given to be 900 tons. So let's call this M sub B, B for bridge. There is a nice little locomotive here going to the left, and this guy is being supported by two piers, some pole type of structures. They are thin, or we can assume that their thickness is negligible. So they will experience only this vertical reaction as this object moves across the bridge. This is the setup. And we are given that this locomotive has weight M sub L equal to 90 tons, and it is at a distance 1/3 of the entire span. So the span is 300 feet, so this is 1/3, 100 feet. A very standard engineering problem. Okay. With that, the question is, what are the reaction forces that will develop along these vertical supports? So let us solve this problem now. Okay. So as always, we are going to start with isolating that bridge so as to identify all the forces acting on it, so that we can write our equations for the total forces and for total external moments or torques. Okay, now this is my isolated bridge. It has some mass and it is uniformly distributed, so the center of mass will be at the geometric center of my bridge. So there will be most certainly a gravitational force M sub B times G, which is, okay, let's not worry about the numbers now. We have the mass or the weight, depending on the units that you want to study, and we have the gravitational force for the mass of this bridge. Now we have this external loading that comes from the weight of this locomotive. It is somewhere here. We have M sub, what do we call it? L times G. Or you can simplify the notation and simply call them W sub L and W sub B. Again, this is just for the sake of convenience for the units. Okay, so these are my external forces. And I have two supports. So I need to remove them from this picture so as to be able to isolate my beam or this bridge. So I need to replace them by some normal forces, like some vertical forces. Okay, let's call this PR1 or support 1, and let's call this P2. This is the setup, and the question is, what are the values of P1 and P2? That's it. Now let us write down the dimensions. So the entire span is 300 feet, and this guy, the center of mass, is at the midpoint. So it will be, sorry for that. So 150. This is 1/3. So this is 100. And this missing part is 50. Now there are at least two ways to do this. And we are going to discuss both of them. Yeah, we have time. I think we can do that. So far, we have seen that our focus for the pivot point was sort of a center of mass or some critical point that is directly related to the turning or tipping action, right? So in this problem, when we write down the torque equation, the sum of all the torques, we can still assume the center of mass of this object to be our pivot point, so we write down all the torques about that point, or we can do something else, which is kind of better, and that method will give us the answers in a faster way. So we will discuss both of them, but let's start with the forces. Okay, now we have sum of external forces to be equal to 0. Again, this is usually or in general a vector equation, but since we have all the forces in upward or downward direction, this is like a one-dimensional problem, so I'm going to ignore the vector symbol on F, but I will assume direction like this. Suppose upward is positive, why not? Now let us write down the expression for the left-hand side, the sum of all the forces. We have P1 in the upward direction, so it is positive. We have W sub B in the downward direction, so it is negative. We have W sub L, the weight of the locomotive in the downward direction, and we have P2 in the upward direction. So P1 plus P2. Okay, now I think it is easier to work with the numbers. We have 900 for this guy, 90 for this one. So 990 tons. This is P1 plus P2. Now let us write down the torque equation. Again, since this is a two-dimensional picture, my torques could be either counterclockwise or clockwise. So I will assume counterclockwise to be positive again. And let us write down all the contributions, assuming that the center of mass is our pivot point. So I'm going to put a superscript here. This means our pivot point is the center of mass, namely this point over here, because that's the original definition of the rotational condition, right? We always consider the motion of the center of mass. Okay, now let us focus on the left-hand side. We have P1 trying to create a torque in the clockwise direction, so it is negative. And the moment arm is 150 feet. Okay, what is the contribution of W sub B for the moment? Perfect. Because it has no moment arm, because it goes right through the pivot point. Okay, we have now W sub L, and it is again trying to create a torque in the clockwise direction, so it is negative W sub L times the moment arm is this portion, right? 50. And now we have the last one, P2, that is trying to rotate my bridge, my object in the counterclockwise direction, so it is trying to create a positive torque. P2 times the moment arm is right here, which is 150. This must be equal to 0. If you plug in the numbers here, okay, let me give you some numbers if I can. Okay. You have 150 here, 150 here. We have this relative minus sign, so if you simplify this, you will get P1 minus P2 to be equal to negative 30 tons. And then you can solve it, right? You have two equations, P1 plus P2 equal to something, P1 minus P2 equal to something. If you add them up, you will get 2P2, 2P1. So I'm really bad with algebra, so let me just cheat. Okay, 480. And P2 will be equal to 510 tons. Now, let's see what happened. We had to use two equations to get these forces. Can you suggest me I'm going to say a better way, a shorter way to get one of the forces, P1 or P2, directly by changing one tiny bit of an assumption about our vector equations, either this one or this one? Yes? That will change the picture a bit, because then we would kind of ignore this point. We would have to consider a joint version of them, but still we would have to write two such equations. It will be the same sort of mathematics, but in a more elaborate attempt, let's say. But very good idea. Anyone else? Yes. Exactly. Perfect. So yes, this is a trick that we could consider. If you now just consider, say, one of the endpoints, when you write down the torque equation, oops, you will immediately eliminate one of the P terms, right? Okay, so this is what we mean. This is just a simplified figure for sake of notation. Let's call this point A, let's call this point B. If I write down all my torques about point A or B, I'm going to get rid of one of the forces already, and I will just have one equation that has one unknown in it, so I can solve it directly. Okay, now if we take the moments about the leftmost point, we are going to have what? We have P1 times 0, because that guy goes through the pivot point, because it will have 0 moment arm. And we have now contribution, some non-trivial contribution from the center, from the weight of the bridge. So we have WB trying to create this clockwise moment with a moment arm of this much, 150. And we have the weight of the locomotive trying to create a torque in the clockwise direction again, so negative, W sub L. And the moment arm is this bit, 200. And we have this P2 trying to create a counterclockwise moment with the entire span as the moment arm. So we have 300. So this is 0. And you can easily solve this equation for P2 now without having to worry about two equations. You don't have to do that. It's not a must. You are not required. But sometimes when you have more forces involved, this is how you could simplify your starting equations, so that you have fewer equations with fewer unknowns in, so you can solve them in a faster method, especially during exams. So I think, okay, we are almost out of time. Yeah, we had this one last example, but Professor Brown said it is okay if I cannot finish everything today. So yeah, okay, for you to think about as a, humble exercise later. I mean, no one does it, but let's say you are bored when you are having a cup of coffee and you want to solve some static problems. I'm just going to drop this, and then you will be able to leave the classroom. So you have this structure, I don't know what you would call it. It's like a ladder. Yeah, this part. And there is a person sitting here. And it's like a symmetric position. And this ladder is standing on some ice, so there is no friction here. And the weight of this person is 900 newtons. You have this apex angle here, 30 degrees. This height is 2. The remaining height is 2. The question is, so we have this cross brace here that will hold this ladder together so that it doesn't just split open on this ice frictionless surface. So the question is, what is the tension that will develop in that piece, in that cross brace piece? Yeah, that will all for me today. So thank you for your kind attention, and we can dismiss.